Hello, everybody. So we're going to move on to lesson number 4, which is going to be on functional groups. So we did talk about functional groups briefly before. These are groups of or moieties or regions on organic molecules that basically give that organic molecule its chemical properties, and mostly its organic properties. So this chart shows you essentially all organic groups that we currently have. So you can see them circled in different colors. Those are supposed to be color coded to represent color coding here is to represent similarities in their function, although none of these two groups are identical, obviously. But you could kind of group them into red, which are hydrocarbons, or blue, which are simple oxygen heteroatomic molecules, or orange, which is sort of sulfur-based or bright orange. So if you just look at the names, we did talk about some of them. So things like alkane, alkyne, alkene, alkyne, alcohol, ether, so on and so forth. So I'm going to go through each of these one by one. As you can see, alkanes only have single bonds. For carbon, alkenes have double bonds in them, and alkynes have triple bonds, and those are all called hydrocarbons, classic hydrocarbons. When we look at this blue region, those are simple oxygenated hydroatomic compounds, so things like alcohol, ether, and epoxides. Um, so alcohols we talked about. Ethers are compounds which have an oxygen in the middle, and they have two carbon groups next to the oxygen. So think of water, H2O, except now in a sort of hydrogen you have carbon that becomes an ether. Epoxides are cyclic ether. So if you actually make a bond between R1, R2, you essentially get an epoxide. Um, Next, we have haloalkanes or alkyl halides. These are essentially coming from mostly either from alkanes or alkynes, or sometimes from some of these guys here, like such as alcohol. But you can actually replace a hydrogen with a halogen, and you would get alkyl halide, aka haloalkane. Again, remember X means halogen. We did talk about these groups here. All of these ones in green are essentially carboxylic group or carbonyl group compounds, aka carboxylic acid relatives or carboxylic acid derivatives. So when we think about these groups, we did talk about aldehydes and ketones and carboxylic acids, and essentially these ones here are going to be your what we call carboxylic acid derivatives. If you think about what's happening with acid anhydride or ester or amide or acyl halide, is that in the case of acid anhydride, you're replacing OH with this group here. In the case of ester, you're replacing OH with this group here. In the case of amide, you're replacing OH with this group here. And in the case of acyl halide, you're replacing OH with an X or a halogen. So essentially, all of these compounds here are actually derived from carboxylic acids, hence the name carboxylic acid derivatives. And finally, at the bottom, we have nitrogen-based compounds. So these are all listed here. The simple ones are called amines. These ones are the ones which have nitrogens with essentially two hydrogen attached to it. But remember, this could be primary amine, secondary amine, or tertiary amine. So you don't have to have hydrogen here. You can have two R groups. If there's a triple bond between carbon nitrogen, that's called a nitrile compound. Otherwise, you will have imine. So imines are the ones which have a carbon nitrogen double bond as opposed to a triple bond. Or you can have carbon nitrogen double bond and a carbon oxygen double bond sequentially, and that's called isocyanate. And finally, we have azo compounds, and those are essentially shown here. There's a double bond between nitrogen and then two R groups attached to it. And finally, we have thiols, and arenes. Thiols are very similar to alcohols. These two are essentially similar in behavior, organic behavior. And if you actually look carefully, you will see that the only difference is that sulfur has been replaced by oxygen here in the alcohol case. Remember, oxygen and sulfur are in the same group, so you do expect similar chemistry between those two groups. So again, thiols. And if you actually look at the name, it also ends with ol as opposed to this one, which is alcohol. Again, it's alcohol, all, thiol, all. And again, these are sort of somewhat similar. And finally, we have A ring groups. A ring groups have essentially benzene rings attached to them. This compound or this molecule, for those of you who are not familiar with it, it's called a benzene ring. Sometimes you draw a benzene ring as shown. Sometimes you show them, sometimes you show it as, sometimes you do this. Essentially, it's a conjugate system. Now, what a conjugate system is that it's a system, it's a conjugate system. A conjugate system, by definition, is a system, these are the same, is a system that has double bonds, one in a sorry, one every other carbon has a double bond. So you can see these two carbons have double bonds, these two carbons have single bonds, then you have a double bond, single bond, double bond, single bond, double bond, single bond, double bond. When you have this sort of back-to-back single double, so that would be another example. These are called conjugate systems, and these conjugate systems are very important in organic chemistry because they demonstrate, unique behaviors. For those of you who are doing UV, ultraviolet spectroscopy for your presentation, you will see how conjugate systems are applicable. I've listed a few charts here for you guys to practice. So what I recommend is that you go through these molecules. These are your hormones. Most of them are your hormones in your body, such as testosterone, estradiol, estrogen. And so look at these hormones and try to figure out which functional groups you see. So I'll just give you one example. If you think about, let's say, norepinephrine, let's take norepinephrine as an example. Let's take norepinephrine as an example. And if you look closely, you will see it has an amine groups. You should know amine group. You should know that's a primary amine. You should write that as, you should write that as, right. You also have this group here. That would be a secondary alcohol. You also have a benzene ring here, so you can actually practice the functional groups using this chart. So go through these molecules, see if you can figure out which functional groups they have. There's more examples down here. These are so above chart are essentially your hormones. These are mostly hormones. These are mostly hormones, and here I've listed a bunch of medications. Now you have, I'm sure you've come across some of these medications in the drugstore. So things like aspirin, aka acetyl salicylic acid, or sometimes called ASA. This guy is also known as ASA. You've seen ibuprofen, aka Advil. Same thing. You have naproxen, or Aleve, or Tylenol, or acetaminophen. Those are, again, interchangeable. So, for example, if you look carefully in the case of Advil, it has a carboxylic group in it. If you look, I guess that's a circle, that's fine. If you look here, you'll see it has a benzene ring, right? Here, in the case of aspirin, you can see it has an ester-like structure right here. It also has a carboxylic group right there. So things like that. Phenol, for example, has an enol. We call that enol group. or enol. I didn't list that up on the top, but when you have an alkene next to an alcohol, it's called an enol group. These are important groups because what happens when you put them next to bases, this one becomes, it loses a proton, and then you form this compound here and becomes enolate. And then it can actually form a conjugate system. So these systems are actually also very stable. Here at the bottom, I'm showing you a bunch of different, what we call nitrogenous bases. So what we call nitrogenous bases used. Actually, I'm going to do this. So these nitrogenous bases, let me just show you this. So at the top, you see U, T, and C, and then at the bottom, you see G and A. So all of these ones on the top are actually called pyrimidines. At the bottom, they're called purines. These are called pyrimidines because they have single rings, right? They're monoring structures, one, one, one. Purines, they are double ringed. There's one ring here, there's another ring here. You can see they're double ringed. There's two purines, Ag, and there's three purines on the top, which are called Cu and T. Now let me give you a mnemonic. Let me give you a mnemonic so that you can never forget. So if you think about pyramids, you know what pyramids are, right? You've seen them in movies. The pyramids of Egypt, for example. So pyramids for pyrene, pyramids are sharp, hence they cut you, right? And then remember, CUT is, oops, CUT is CUT, cut. The pyramids, pyrimidine, are sharp, so they can cut you. Here, purine, if you think about Ag, Ag in the periodic table, it's a symbol. So A for A, G for G, is a symbol for pure silver. You guys see where this is going? So pure as in purine, pure as in purine, silver as in Ag. So it's pure silver in the periodic table. This is a symbol of silver or pure silver in periodic table. Again, take a look at these compounds, see if you can figure out any familiar functional groups. So, for example, this one has an amide in it, as you can see here. So things like this. Now, for those of you taking biology, it's important to know that uracil is only found in RNA only, and then thymine is only found in DNA. That's also important to know. Okay, and then finally we have these, what we call, if you remember, these again, these are carbohydrates, right? Because they only have carbon, oxygen, and hydrogen. So these are carbohydrates, aka sometimes we just call them saccharides. Sometimes we call them sugars. And what we have here is, let me just put this one here. What we have here are essentially both of these two are what we call pentoses, hence 5 carbon molecules, right? This one, let me actually move this over. So if you look at, for example, so they all have 5 carbon. Let me just highlight the carbons for you. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And let me actually number them too. So this is 1, 2, 3, 4, 5, 2, 3, 4, 5. If you look carefully at um uh, carbon number 2, if you look carefully at carbon number 2, so here here you have you have hydrogen and no oxygen, no oxygen, hence the name hence the name deoxy. Remember, oxy means oxygen, D means no or absent. If at carbon number 2 you have no oxygen, the sugar or the pentose is called deoxyribose. Okay, these are pentoses. So deoxyribose is one, and then you have ribose. If, however, you have oxygen, you're not deoxy, you have it, you're just simply ribose. And then finally, I'm showing you some amino acids. So these are basically 20 amino acids that we have in our body. Again, look through these R groups. Let me show you. Um, let me show you the overall structure of amino acid. So so when you look at amino acids, basically that's how they look like. Okay, so I'm going to draw them in a simple format. Okay, basically, an amino acid has the following regions. It has a carboxylic region. It has an amino region, amino group. It has an R group, and it has a hydrogen. Okay. So first of all, let's see what's what. So this one here I'm showing you is a carboxylic moiety. This is called an R group. This is called the amine or amino group. Amino moiety, and that's just hydrogen. Basically, we have 20 different R groups. Hence 20 different amino acids, right? That's why you have 20. Now, on the table below, I'm showing you these 20 amino acids, which you can see here, right? And you can see it's the R groups that are different. Everything else is the same. And depending on the R group, you will have different type of amino acid. So if you look, for example, to this part of the chart, you have nonpolar R groups, such as hydrogen, methyl group, isobutyl group, isopropyl group, sorry. There's a group here, there's a group here. So these are all what we call, again, non-polar groups. If you look at these ones here, these are, for example, positively charged amino acids. These folks here are polar uncharged group amino acids. These are negatively charged, and these are what we call non-polar aromatic are groups. Now, what's important for you at this point is to be able to recognize different structures in these R groups, different functional groups in the R groups, and then be able to tell why that R group or that functional group uh, contributes to the type of amino acid that you see, right? So let's do that. Let's use these ones here. So lysine, arginine, histidine are the three what we call positively charged basic amino acids. These are also called basic amino acids. So these three sometimes are called, AKA, basic amino acids. And then down here, these are sometimes called acidic amino acids. So let's see why. Well, if you look carefully, what you will see is that in all of these, in all three of these positively charged amino acids, right? These are positively charged. That first of all, they have positive charges. You can see that here, here, and here. But secondly, you see that they have amine groups, right? So the R groups have amine groups in them. So I'm just going to say NR2, right? That's what makes them mostly basic as well as positively charged, right? If you look at these ones down here, you see that they mostly have carboxylic groups in their R groups, okay, which makes them acidic. So where am I talking about? I'm talking about this part and this part. So both aspartate and glutamate have carboxylic moieties, which makes both of these two what we call acidic or negatively charged amino acids, whereas these two are mostly nitrogen or nitrogenous or nitrogen based, right? Uh, these are your nonpolar aromatic rings. Remember, aromatic usually means you have it usually means it usually means you have something like this. Usually, not always. You probably have a benzene ring somewhere. This is an aromatic compound. Okay, now we'll talk about aromaticity later on. Uh, to be aromatic, you have to fulfill some criteria. There are some requirements, but let's just say for now, if you look at something that looks like a benzene ring, that you should expect aromaticity, or hence the name aromatic. Down here, you've got polar uncharged. So these are not charged, these are not basic or acidic, and you can see there's no net charge on them. Okay. Uh, and if you look closely, what makes them polar essentially are depending on amino acid. You have an alcohol group here, you have an alcohol group here, you have a thiol group here. Remember, SH was thiol. Here you have an amide group. Remember, this is amide. Here you have another amide group, and then this one is cyclic. Now, proline is a bit different. Proline causes kinks in amino acids because it has a ring structure, but it still counts as non-polar. Polar uncharged. Um, remember, this is not part of the R group. This is part of the amino group, so the net charge is still 0. When you say charged, here you're talking about net charge, right? So here, here, and here, the net charge is 0. Here, the net charge is positive. Here, the net charge is negative. And when we say the net charge, we're talking about net charge at or under what we call physiological pH, which is roughly around 7.35 to 7.45. Essentially, that's the range of a normal physiological pH. If you change the pH for some of these amino acids, you will potentially change their charges, right? So you could potentially actually make glutamate uh, make it have a zero charge, negative charge, neutral charge or zero charge. Essentially, you could protonate this one, and then you could have zero charge. Same thing here. You could actually lose a proton. This could become NH. Uh, sorry, sorry. This could become NH as shown. And then in that case, you would lose a positive charge and you would be neutral because you would have plus minus and it would give you neutral. So you could change the charge of these, any of these, potentially if you change the pH of the solution where you find these amino acids. Okay, so that's it for this lesson. I'll see you guys over on the next.